We're here in Lind Coulee. We're looking at some new exposures that I hadn't visited before in alluvial material in these cut banks. And so I just wanted to bring you along, kind of look over my shoulder as I wrestle with geology as I encounter it for the first time. So there's 4 units here. The lowest unit is a sequence of alluvial sediments, sort of a gray-green set of fine-grained sediments. Over that is a pink, sandy, silty unit with lots of soil features. Above that is a calcrete, a thick ledge of calcrete. And then on top of that are 4 tushy beds, so late Wisconsin flood deposits. So come along with me and we'll check out Lind Coulee. I'm here at Lind Coulee. Highway 17 is right there, the bridge going to Moses Lake north or Othello to the south. And there's this prominent outcrop that you can see from the road that's capped by this thick calcrete. So the stratigraphy starts out with some overbank sediments and these really conspicuous white stripes that run through this gray-green silty overbank stuff, sort of incipient wetland soils. Those white stripes might be ash beds. Above that you have this highly irregular surface, and then on top of that these irregular bodies of sandy pink, sand and silt, pinky sediment. Then above that you get into this gray-green soil with a blocky peds, sort of again a lowland wetland soil. So we're in sort of a floodplain environment, right? And then you grade upwards into calcrete, which is almost 2 meters thick. So we're sort of hovering around the shoreline here, right? This is sort of a wetland transition upward to dryland environment. Low relief landscape. Competition between soil formation and wetland. Sorry, I can hardly talk. It's only about 38 degrees out here and I've got a t-shirt on, so I'm freezing in the shade. Another thing you see here is these little fracture sets, these orthogonal fracture sets, so vertical and horizontal, and they'll be cemented, and it's a very distinctive pattern that appears in certain layers. You can see this orthogonal crack pattern, and sometimes that's something to use as a correlation device. Not always, but sometimes it is. Another thing is, you know, these sands, this is a sandy unit here, and then a silty overbank. This is really a soil trying to form here. See the little prisms? So this is a flooding surface. So the energy has increased here, right? We've got flowing water above and sort of muck below, and that we can follow that flooding surface along. And you know, it's just sort of telling you that you've got a sluggish fluvial environment, but there are pulses of, you know, channel avulsion, channel activity. You got a change in energy regime here and there, but in general, it's pretty sluggish, pretty low energy. Once in a while, you get this pink unit that comes in. There's 2 of them here. There's 2. This one and then one slightly above. But you get a highly irregular base, and this is a sandier unit that comes and goes. But you got a distinct, you know, erosional base on this thing. It's forming these little channels. And everywhere you see it, it's erosional. Now, it's been overprinted by soil processes, but you can still see there's a lot of little channeling going on. But they're small channels, right? I think it represents pulses of energy, pulses of flow through this sort of sluggish muck. I interpret that as floods. I don't know if those are mega floods. Whatever's below the calcretes changes. Here it's a wetland and overbank soil. Other places it'll be alluvial fan gravels. Other places it'll be basalt bedrock. But wherever you get these calcretes, you get these pinky, rooty, goofy, sandy silts. The other thing that I always like to find is, of course, clastic dikes. And there are a few thin sheeted dikes that cut this section. They're wedge shaped, they taper downwards. Some of them pinch out right here. There aren't that many, but like, for example, this one, you can trace it up and it cuts right from the surface. You can follow that crack. See, that's a little dike there. So this dike is filled with silt and sand. It's sandy, and that's unconsolidated. That's tushy bed sediment. Yeah, no question. And it cuts through the whole section here, and that dike in particular goes below my feet. So it's cutting 3 or 4 meters a section here, and other ones do the same, or they pinch out. This Othello area it's just great. Othello is the Rodney Dangerfield of geology. It gets no respect. Everybody hates driving through Moses Lake. But there's some pretty cool stuff going on here. And you should stop. Calcrete and caliche are subsoils, right? They're paleosols. So they're telling you you've got a dryland environment. You've got calcium carbonate available to soils. And because they're so thick, they're telling you you've got a great deal of stability in the landscape right here. Some of these textures and some of these sort of stringers and the overall thickness of this blocky advanced stage calcrete does hint at some interplay with groundwater. So we're hovering around the water table here, and with these thick calcretes, I think we're just sitting right there in the capillary fringe. In order to create calcrete, you have to have an awful lot of evapotranspiration. Year to year, you're just drawing an enormous amount of water out of the sediment. So that means a couple things. It means you've got a lot of water pulsing into the system at some point during the year. You have long periods of fairly dry conditions where that water can be drawn off to the atmosphere. So you have to have considerable moisture some of the time, and then have longer periods desiccating that soil, or evapotranspiring that moisture out of the soil. You also have to have a landscape that's not being actively eroded and not being actively buried. So you're looking at a geomorphically stable surface that's persisted over very, very long time frames. The important thing is stability. This was a stable surface, post-Pliocene, post-Ringgold surface that was sitting here doing not a whole lot. A tectonically stable landscape right here next to the Yakima Fold Belt. This surface was aggrading, but slowly, and it just looks like a very stable floodplain that was sitting here for quite a long time. And in order to pile up 2 meters of calcrete, the time frame for that has got to be hundreds of thousands of years. probably 3, 4, 5, 600,000 years, maybe more, maybe twice that much. But I guess I'm comfortable with saying, you know, maybe as much as 500,000. I'm gonna go over there next. So I was right over here, and then now I'm on the other side of Coulee, and checking out these calcretes exposed in these cut banks. So I hope you can see that with this cloudy light. One of the things you'll see in these calcretes is a different sort of bedding. The parting is pretty fine here. It looks thin bedded, as opposed to here where you have those 2-inch thick, 3-inch thick, blocky, that blocky look. And that's pretty common. The top 20 centimeters or so of a lot of these thick calcretes are blockier, and they're more well cemented, and so they tend to take on this this coarser. It's not bedding, but it kind of appears like bedding. Yeah, so blocky uppers, and then as you move down through the same, you know, calcrete body, might be more than one soil here, but commonly you'll see the bedding sort of thin. There's probably a technical term, but I call this like heavy stringers, right? These horizontal wavy ribbons of calcium carbonate are overprinting the parent material, which are these darker places that are still left. And this is loess, or sandy, slightly sandy silt. So the parent material is still apparent, even though it's heavily overprinted by these stringers. And then as you move up, the calcrete starts to take over, and you lose a whole lot of information about the parent material. It's just been fully plugged with calcium carbonate. So this is concrete hard, and right here it's still a little disaggregated, and I'm not sure if that's an original condition or if that happens over time where some dissolution sort of weakens it. These are barriers to infiltration, absolutely, and give farmers a problem. You can see you've only got about 30 centimeters of modern windblown soil on top of that where those grasses are, and so you're gonna have to rip this to significant depth if you're farming on top of this surface. It's just fun coming out here, you know, and discovering stuff. I don't think anybody's been here in years. Nobody's ever written up this outcrop, and it extends for, you know, 300 meters, and it's 4 or 5 meters a section. Here's a good look at that pinky stuff. So this is classic. I mean, you got these little filaments, and then these little roots, so little tubes, and this sort of background of wispy calcium carbonate. You've got obvious, you know, up to an inch, you know, 2 centimeter diameter tubes. You got little rip ups of cemented loss. Little these are those little cicada burrows that get ripped up and act like a gravel. And then you've got an irregular body of it that follows this surface. There's another look at that pink sandy unit, and here you can see there's all sorts of little chips, rip up class, little chips of calcium carbonate, and it's a sandy bed. You can tell it's sandy just by looking at it, but you can definitely feel it too. You could even pull out a grain size chart. Check out some of these root casts, cemented burrow forms. I mean, that's cemented. I think that's a rodent burrow, just like this is, just like this is. But you also see, what else can we see here? Yeah, these are rodent burrows too. So they get backfilled and then they get cemented. There's a good one. They're almost, boy, that's really in there. They're almost tree-like, but they are burrows. And there's some cicada. One of the challenges of working in these units, this post-ringgold alluvium and paleosol sequence, is that there's a broad overlap in time. Well, let me back up. So the Columbia River, the ancestral Columbia River, and the ancestral Snake Clearwater system reworked the top of the Ringgold in places, especially in the Pasco Basin and areas nearby. That alluvial unit that sits on top unconformably over the Ringgold is overprinted by Calcrete. The Hanford guys call it the Pliopleistocene unit. It's pretty clear it's a Pleistocene unit, but because some of the soils overprint parent material that is Pliocene in age, that Pliopleistocene term sneaks in there. But these calcretes are Pleistocene age. So one of the challenges is that the age of these calcretes and these parent materials into which they're developed overlap with scabland flooding. And so there's sort of a challenge to tease out, well, what are these sediments showing us? Are these sandy units just alluvium? Or are these sandy units interrupting a background of alluvial activity, right? Are sandy units in this section pulses of flooding coming through the landscape, or are they just the usual valley alluvium, streams doing their thing, draining the Palouse slope and this part of the channel scablands? The evidence is mounting for an ancient flood record that is, over the past several 100,000 years. We know we've got Ice Age floods scouring the landscape. It's just we don't have a great record preserved because the younger floods, the Missoula floods, those that are essentially younger than 20,000 years, have removed most of that evidence or buried it. Sections like this, where you have a calcrete ledge with this sandy, pink, silty, burrowed sediment, you'll often find rip-ups. It's clear that this is not loess, even though it's got cicada burrows in it, even though it's got a pretty good component of silt. This is water-transported sediment. And because these pink layers, these interesting sandy layers come in consistently across the landscape, unlike the background of the alluvial material that changes everywhere you go, these sandy units, these pinky, sandy, burrowed, trace fossil rich units are consistent in the stratigraphy. They show up in the same places, and they just vary in grain size and a little bit in character. But this kind of, these chips, these rip-up chips, will grade laterally into boulder gravels sometimes. And then if you go the other way, they'll grade into a nodular loess. So there's the problem. You've got ambiguous information. You've definitely got flowing water that's bringing this stuff in. But is it flood water or is it just stream water? Is it part of the alluvial system or is it something perturbing the alluvial system? So these are really the key. Sometimes you see on top of the Calcrete, you'll see gravel, and this is just that. So we're seeing rip-ups of Calcrete and cobbles of basalt that are encrusted with a rind of calcium carbonate. So this is a gravel. The reason I know that, or I'm confident about that, is because here's some flood rhythmites and boulder gravels with coarse sand making this slope. So pretty cool spot right here. We'll check out these rhythmites right above. The Calcrete ledge is right below my feet. It's right down there. See it on the rim forming that shadow. And then right above that are 4 tushy beds. And these are pretty cool because you see some nice soft sediment deformation in here. So this would be the upper portion of this rhythmite. The lower portion is sandier and gravelly, and it's forming this slope. But we're looking at the slackwater portion here. And the first part of it, you can see, is planar, right? That bedding is just flat lying. And then at some point, it just changes, and you've got a lot of drag on the system, and you're deforming it. So that deformation is caused by this gravel, the next flood, or some might argue the next pulse within the flood, coming along, depositing higher energy flow on this soupy sediment and dragging it, deforming it, loading it, and causing these load casts and flame structures. This is so common in the tushy beds, and people don't talk about it a whole lot. I think for the most part because, you know, there's only like 3 outcrops that people ever look at in the whole channeled scabland. And you know, if you just go to Tushy River Road, you don't see the full suite of features that are actually more typical of flood rhythmites like this. If you just stay in those same places where all the tourists are, you just miss out on some things. So pretty interesting. This gravel has also got, you know, our familiar basalt, old basalt. So here's some weathered basalt class. We've also got this brown mudstone, probably ringgold, slightly cemented. You know, essentially what we're doing is ripping up an old sandstone, Pliocene sandstone there. Let's see what else we got here. There's part of that. That might be Vantage sandstone, I don't know. Might just be out of the upper ringgold too. There's that. And then these gray-green mudstones that crumble whenever you pull them out, or these white clay stones that are always compact, they're hard. I don't know if they're ashy or not, but they're real fine-grained, silty, clayey. So larger blobs of clasts, I should say, of stratified sedimentary rock, but not real old rock. This is, you know, barely put together. But it's being tumbled along in the floods with, you know, competent hard bedrock along with a bunch of sand. So pretty cool. There's 4 flood rhythmites exposed here on top of that Calcrete ledge. So here's an example of where that question arises. Is this section recording or preserving a flood record or is it just an alluvial record? Is it something exciting, or is it just something, background and kind of boring? Well, all right, so let's walk down through the section here. So we've got our meter thick, or about 80 centimeters of Calcrete here. And then we walk down into the shadows, and I'll try to get in here a little closer to get a better look. And we've got horizontal stringers, cementation, overprinting, a sandy, nodular unit. These little holes are modern insects burrowing through there, but you see the root casts, you see the stringers, you got this typical brownie pink look to that unit. And then below that, in the sun, we've got something different. So these look like those round cicada burrows, and yes, they are. But if I back up a little, that's a cross-bedded sand. Those are basaltic grains, coarse sand grains verging on pebbles. And these little these little cicada casts are functioning as clasts here. So these are acting like pebbles. It's kind of cool. So let's keep working our way down. Basaltic clasts in a sandy matrix with pretty clear cross-bedded bed forms. So we're looking at water deposited stuff, water and less energetic water, and then a soil developed on top of that. So is this evidence of flooding, or is this evidence of, ancestral Crab Creek? I don't even know what creek this is. Probably Crab Creek? Flowing through Coulee. So 2 meters below that Calcrete, over there, I was just finding nodular, sandy, pinky material. 2 meters below that cap here, I'm finding cross-bedded sands that contain mostly basaltic clasts, but certain some other clasts in there too. So the test might be to find exotic clasts in this deposit, and if I could do that, well, that might say something about the nature of that sediment. So we've been to the field, and now we're back in the office, and I'm looking at my notes from the day. So what do we see here? Well, there's a lot of continuity in these sections. Let's start at the bottom. The green stuff is overbank alluvium in wetland soils, interrupted by maybe slightly sandier or fully sandier channels, but a sluggish fluvial environment. Now we know that this is latest Pliocene or the earlier portion of the Pleistocene. So this is essentially Ringgold or just after Ringgold time. So we're talking, 3 million, 2 million, right in there. Shifting over here to the cutbank sites where we had those tushy beds exposed, we know that above this brick pattern is the Calcrete ledge. Above that, we know we have late Wisconsin tushy beds. So late Wisconsin floods, Missoula floods. And then on top of that, dune sand, Holocene sand dunes. So we've got the base of the late Wisconsin, and we've sort of got the top of the latest Pliocene, maybe early Pleistocene. And what's between is this Calcrete and these pink units, and possibly this channel sand, this cross-bedded pebbly, gravelly sand. We're trying to answer the question of whether or not these pink units are distal flood units. Are these flood sediments that are coming through the landscape, but we're just far enough off the high energy channels in the pre-Wisconsin period? Or are these pink units essentially just slightly higher energy versions of the floodplain system that we know we're very near? You know, we've certainly got erosional surfaces on top of calcretes. We've certainly got rip-up clasts and flowing water in these pink units. They're overprinted by later soil development, later burrowing. They definitely interrupt the background sedimentation, but nothing says full-on megaflood energies. Even this, the highest energy deposit that's here, still is pretty ambiguous. This feels like side stream deposits. This isn't a big river. This feels like a pretty small stream, probably not unlike Crab Creek is today, carrying sand, carrying pebbles, carrying small cobbles. It's hard to say for sure that these pink units represent the distal facies of megaflood deposits. However, they are at a position in the stratigraphy that is awfully curious, because elsewhere, very nearby, in this same stratigraphic position, I have boulder gravels with exotic clasts that are clearly flood deposits, pre-late Wisconsin flood deposits. So that's the nut of the problem. Erica Medley's work with Scott Burns at Portland State a few years ago, they came through and sampled these calcretes, 25 sites in this part of the world, and looked at these sediments and basically called all of these pink units flood deposits. My own findings confirm that there are boulder gravels in this same stratigraphic position. Here's my correlation of those columns. I've left the alluvium below this level. I've left that cross-bedded sand in the alluvial section. I've got one flood unit, or one pink unit coming through, capped by a soil. A second flood coming through, capped by a thicker soil, a much longer period of time. And then much later, tushy beds, so late Wisconsin floods, truncating that calcrete, and just so happens that they're not present right at that scarp, but they're nearby. We know tushy beds lie on top of this from other outcrops in the area, and these dikes are filled with tushy bed sediment. So that's it. So the alluvial section stays down there. I'm bringing 2 pulses of tentatively flood sediment separated by soils, calcic paleosols, petrocalcic horizons. They often lens out laterally, so this is not an uncomfortable relationship at all here. This is very typical. These thinner calcretes especially come and go as sort of lens-shaped bodies. The upper calcrete ledge is continuous, is a blanket across the landscape. It's probably a welded soil. There's probably more than one soil in that body of calcrete, but that's how you see it on the landscape, and I'm not going to pull out individual units anytime soon in those ledges. So that's my correlation. This is literally how I work. This is 1 half-day's work in the field, and the results don't solve the problem, but they lend insight to the larger question of what is the origin of these pink units as they sit below these calcrete ledges and on top of a ringled or slightly post-ringled alluvial system. All right, hope you learned something. Thanks for watching.